Okay, good morning, everybody. I think we'll let folks who are walking around join us in here, but we'll try to get going and stay on schedule. Welcome to Minnesota, everybody. I'm Peter Neff. I'm an assistant research professor here at the University of Minnesota in the Department of Soil, Water, and Climate. Really jazzed to have everybody here up at Cloquet Forestry Center. I'll give a little bit of an introduction to the WAIS Workshop and what we're going to be up to the next few days, science-wise, I suppose. And then we have Andy David, the director of the center, is going to give us a little bit of a sense of where we are and what the university gets up to here at the center. Yeah, we'll try to go over some sort of logistical things here as I introduce things, and my fellow co-organizers can hop in if I forget anything that I'm supposed to mention. And I do want to acknowledge that I am the local host, but I'm just one of the WAIS organizing committee members. So if you guys, Matt, Brooke, Knut, Mickey, Lauren, you guys want to raise your hand, stand up, say hi. So please don't give me full credit for organizing all of this. Matt does the lion's share, and Angela from Colorado Schools of Mines have done an awesome job getting things together. So thanks to Matt and Angela, although I guess jury's out. We'll see how it goes. Yeah. Awesome. I wanted to start, as we think about Antarctic science and Antarctica here in Minnesota, give you a little sense of some of the history of University of Minnesota research and sort of regional Minnesotans and Midwesterners in Antarctica. So if you take a look at the map of Antarctica, there are a sprinkling of University of Minnesota names, mostly from early scientific expeditions in the 50s and 60s. A lot of mapping in the Ellsworth Mountains and out in the Jones Mountains towards the Bellingshausen Sea coast of West Antarctica. So some really cool early science getting way out in West Antarctica in the first couple of years of sort of the modern era of Antarctic science.
How does Teal get to be Minnesota? Isn't that Wisconsin?
He was up until the last year of his life, and he was then a University of Minnesota employee.
I don't know that.
Sorry, we're gonna take it. I did have a note. I have a note coming up about Teal as well, but I was gonna gloss over that whole part, Sridhar. But we do have one of the more accomplished University of Minnesota alumni as far as what one does during their PhD. Mapping an entire mountain range in Antarctica is pretty impressive for Bob Rutford. He happened to grow up just like 5 houses down from the house that I live in St. Paul now, which is some fun local history. There are some other firsts from around the region. So the first woman as a scientific station leader at McMurdo was Mary Alice McWhinney from DePaul University, and then just down the road here, Sister Mary Odile Cahoon joined her wintering, the first 2 women to overwinter at McMurdo in 1974. We also have connections with George W. Gibbs, the first African American to set foot on Antarctica as part of the 3rd Bird Expedition. He came back to Minnesota, got a degree at the University of Minnesota, and then became a really key community member in Rochester, a civil rights and civic leader for the rest of his life there. Teal was a University of Minnesota professor before he sadly lost his life in Antarctica, but he in these early days of Antarctica, the really pioneering measurements that were made on traverses, taking seismic observations to answer really fundamental questions of such as whether or not Antarctica is one continent or two. So I won't dwell on these sorts of things, but there's some really cool history, and I'd be happy to talk to folks further about this. And if you do enjoy one of the better views in McMurdo, in the library, the Prairie Science Facility, is the Teal Library, named after Ed Teal. So I guess to have some more sort of logistical introductions to do here in the next 10 minutes. Why is this buzzing at me, Matt? Okay, it buzzes at you periodically, just FYI. So we're here to talk about the West Antarctic ice sheet and understanding its, I suppose, past, present, and future behavior, because that has really important societal implications, mostly with respect to sea level rise. And so I took some of these keywords from the 2016 WAIS science plan, which we're hoping to revisit later today as we think about drafting an updated plan on that plan. I grabbed the International Thwaites Glacier Project, but this could just as easily be a figure from 1978, sort of spanning that amount of time that we've been really thinking about these potentially rapid, really consequential behaviors of the West Antarctic ice sheet. So with the WAIS Workshop, we hope to foster the community here and connect across all of the various things that we're studying, the drivers, the processes, the boundary conditions that affect the behavior of the West Antarctic ice sheet system. So hopefully, as we're all giving our presentations and sharing our posters, we can connect a lot of those ideas in the discussion format that we typically have at WAIS Workshop. So we'll have, I suppose I can get the schedule up here. We'll have 10-minute talks across the board this week, and we will hold questions until the end of a block of speakers, and then we have 15 to 20 minutes of discussion at the end of each section, and that's we'll have everybody come up and ask questions and hopefully start connecting across all of our work and sort of synthesizing things there. So today we'll get right into talks after we have an introduction from Andrew David, the director of the Cloquet Forestry Center. We have refreshment breaks in the morning and the afternoon, so 10:20 will be our first break today. Lunch is at 12:15 in the dining hall. Another refreshment break at 3 to 3:30. Then we'll hop into a sort of mini workshop with some breakouts to talk about the waste science plan. We thought that we would spend time on that all together rather than leaving it to any smaller group. So it does take the place of some of the community health focus that we've done in the past couple of years. But hopefully we can holistically incorporate all of that into our discussion of the waste science plan. And then I'd probably get back to having a sort of community health speaker next year. We also have early career and mid to senior career breakouts this evening after dinner. So dinner's again in the dining hall, 5:30 to 6:45. That's after the poster session. Sorry, I'm bouncing around a little bit. I think that's all on that. We have guidelines for all of the conveners that we've invited to come moderate sessions to try to keep everybody on time and make sure that we have a healthy balance of discussion and don't have any dominance of single voices and things like that. So we'll try to make sure that those folks that we did tap to be conveners of sessions, that we empower you to lead your session and keep us on track. What else am I missing here, Matt? Right, we do have QR codes taped all around for student evaluations. There are prizes. Do we have anybody who could model prizes from previous years? Marianne has a backpack, the WAIS Workshop backpack. Ooh. So everybody can be a judge for that. So the more folks that do that will help in the adjudication process. Oh, nice. Thanks. Yeah, thanks, Kelly. And I did a little breakdown of who we are here. So I suppose I maybe should have put the numbers up here, but we're got a great balance of career stages this year. So we can see in orange there, we're heavily PhD centered. I think it was 40-something, 42, 45 PhD students. And then 15 or so sort of mid and senior folks, and a larger contingent of recent PhDs. I suppose that's postdoc stage. And then a mix of other people. We have some NSF and NASA representatives here today. It'll give us some perspective and be here for discussions as well. I feel like that's most of what I was up here to cover. So we're going to get right into science sessions after we have an introduction from Andrew David. If I haven't forgotten anything, I think we'll just welcome Andrew. If you can come introduce us to where we are here in Cloquet.
Gentle, polite applause. This is nice. Thank you. And I'm going to, as long as this is on, I'm going to tip it so I can use it. Welcome to the Cloquet Forestry Center. My name is Andrew David. I'm the director here. I also have an academic appointment in forest resources on the St. Paul campus. And Peter asked me, hey, can you give us just a little bit of an announcement, some words to kind of help place you and tell you a little bit about the university and what it's doing here? And I said, yeah, I can do that. I've done that on a few occasions. So, they had a slide up there with who is here, and that's okay. I'll just kind of roll with that. If I ask you where you're at, you'd probably tell me, I'm at the Cloquet Forestry Center. It's kind of outside Cloquet. It's not too far from Duluth. We're right over by the big lake. It's like, yeah, you're absolutely right. And there's a history here that helps place you, and you should know a little bit about it. So this land is the ancestral home for one of the Anishinaabe tribes. And they're known today, we know them and they know themselves as Fond du Lac. And that's really a name for both the people and the land. And loosely translated from the French, it's basically the bottom of the lake. Okay, and not because it's at literal bottom, but at the south end. And we're referring to the south end of Lake Superior. What we know today as Lake Superior, the big lake. And for millennia, they managed this land. They lived here. This was kind of summer quarters. And in the winter and other seasons, they were up near the Duluth and Superior area. But literally, you are on unceded land of the Fond du Lac, part of the Fond du Lac Reservation. And to make let me just say, for millennia, they managed this land and the plants and the animals that were here for their benefit. And they did so in a way that demonstrated a keen knowledge of both the plants and that land and those animals, and managed them for their benefit. Right around, and I should say, in the 1800s, 1837, 1854, they signed treaties with the U.S. government. And that last treaty in 1854 set up a reservation for them, unceded lands, and then ceded territories for which they retained rights to hunt, fish, and gather. In 1909, this land came to the university as part of federal legislation. And since that time, Fond du Lac has insisted that that land be returned to them. That incessant ask, that persistent ask, resulted in March in the regents of the University of Minnesota deciding that it was best to return this land without preconditions. So since about 1909, the university has had access to this land, and we have, and I say we in terms of the university, done research, done teaching, done professional development, and a meeting like this is just considered professional development. We've put infrastructure here. We've educated foresters, natural resource professionals. We've had a long litany, and everyone keeps track of their pubs, right? You all have done that. You've got CVs. We know how this works. We've got a whole litany of all the things we've published as a function of work and research that's been done here. At this point, we are working with FDL to think about what the future of this place looks like. Without preconditions means that we're entering those discussions without an idea or without a demand or an ask. That's very difficult for the university to do. If you come from a place that's large bureaucracy, you have a sense for how that works, how completely different that is. So, as you are here for the next few days, thinking about, exchanging information, presenting what you know, gathering information about what others know, thinking about what you are going to do next or what should be done next, realize that there are people here doing the same thing, thinking about what this place will look like, exchanging information between two different groups, thinking about how we move forward, and the university thinking about what are its options. We may not have an ideal solution, but we're working towards the best solution possible, hopefully for both sides. And I say sides, and that makes it sound confrontational. This has actually gone about as well as one could hope. So, with that, as you sit here at the bottom of the lake on the ancestral homes of the Fond du Lac, recognize that all sorts of work is being done not only here, but amongst yourselves. Enjoy your presentations, enjoy your exchange of knowledge, and hopefully, I know this is gonna happen. I live in Grand Rapids, which is about an hour and 15 minutes west of here. And when I got up this morning, it was beautiful cloudless skies. In about 2-3 hours, that's gonna be here. And in this place, you're here at a beautiful time. It's gonna pop. So get out, enjoy yourselves, take some walks. There are a number of trails nearby. But do that professional development. Think about where you're at. Thank you, Peter.
Yeah, thank you. Awesome. Well, that's a great grounding for us. We have 10 minutes until the beginning of the first talk on the agenda. Does anybody have any questions logistically about what we're up to the next few days? I suppose the pure basics are that there are bathrooms sprinkled up and down the halls here, men's, women's, and all gender. I hope everybody had everything they needed in their cabins. There is a linen room to exchange anything if you need to. Just come to me or Matt or any of the organizers if you have any questions or needs. Hopefully the ride situation between hotels was okay this morning. Did anybody have any trouble? I guess everybody's here, so everybody that's here didn't have huge trouble. Somebody's texting me right now. I don't know. Okay, well, let us know. And, oh, right. Matt's motioning to the Pac-Man on our name tags, which is a reminder that we want to be open to everybody in our circles of conversation and always try to open up for new folks who are looking to join in the conversation. So we're trying to foster community here so that we are all able to succeed in our careers and gain additional knowledge and combine what we all know about the processes, drivers, and behaviors of the West Antarctic ice sheet to better understand where it's headed in this changing world. I suppose it makes sense to just get into the session. So if we could have our first conveners come up, and I'm forgetting who that is, but we can switch. Okay, you guys are there. Do you have the slides? I do see that. Yeah, so posters are just up and yeah, ready to be presented at any time. Any coffee break is a poster session. We have poster session earmarked each afternoon, evening. Yeah, great question. Okay, I think without further ado, we're ready. We got Johnny Kingslake as our first speaker.
Good morning, everyone. Thank you so much for allowing me to. I actually thought minutes and 2 questions. Actually, all my slides, so that's good. So I'm from Lamont Doherty Earth Observatory, Columbia University, and my first slide is all these different logos. We've got a huge collection of different authors here because we're going to be talking about 3 different ongoing and past projects, and I'm going to also summarize 2 exciting new projects. And the theme throughout is this phase-sensitive radar and how we've been using it for measurements of englacial strain, so how the ice deforms internally, in a slightly different way in which the radar was originally developed. And also, these projects are applying this technique in a diversity of different glacial settings compared to where they have been used before. Maybe I have a pointer? Maybe not. Okay, so why I might be interested in glacial strain? So on the left, that map of Antarctica is an inverted field where somebody has used a ice flow model to try and back out what's going on with sliding at the bed. And inherent in that procedure is some assumption or some simulation of englacial strain, because the observations you're using to invert for those properties at the bed or the velocity of the sliding at the bed, these observations are at the surface and the properties at the bed, so you're going to have to make some connection there, and you're making an assumption or a simulation of that, and that's often kind of untested. So that's one reason you may want to be able to measure glacial strain. On the bottom right, we've got a picture of some superglacial lakes, and that's an example where these, and you may know these superglacial lakes in Greenland and sometimes maybe in Antarctica, drain through the ice and cause deformation locally. So that's an example where, whereas the inverted field on the left is a spatial pattern of englacial strain, which you might want to know. The picture on the bottom right is an example of a time when lake straining might cause a temporal change in glacial strain that you might want to know. And so that's a setting where you want to ideally be able to measure glacial strain and not try to back it out from surface observations. And then even in ice shelves, the same can be true. So we're used to thinking of ice shelves as being in plug flow, meaning that the glacial strain is pretty simplistic, it's uniform vertically. But in some places where, for example, the thickness of the ice changes very rapidly in space, like around a channel, shown in the top right, you might expect actual deviations from plug flow, and you may want to be able to measure those things. So, but traditionally it's been very difficult to measure glacial strain. You have to drill a borehole, or you have to and install instrumentation potentially, and it's been a thing which glaciologists have been doing for many decades. So then along at some point in the last 15 or 20 years, depending on when you count the beginning of this development, people started developing these radio echo sounders which could measure the position of englacial reflectors very precisely. Or to speak more precisely, you can measure the change in the relative position of reflectors. The change between measurements taken over a long period, or maybe just between measurements taken with different configurations. So a little while back, I did some of this with the old version of AP-Res. And people who know the differences between these 2 radars, these phase-sensitive radio echo sounders, I'm just going to bulk them together for this talk. So AP-Res is the newer one, and P-Res is the older one. I'm not going to distinguish, really. But I use one of these radar systems to measure glacial velocities and therefore strain in a very simple place, like an ice divide, which is what's shown in the middle. That's the velocity field. And those ice divides are very good for that. There's not much sliding, for example. But now we want to move on, and the rest of the talk is about applying the same technique in more diverse settings. Okay, so that's the little cartoon. What I'm showing is basically these layers deform with the ice as it moves, and we can measure that very precisely. Okay, so I've got 3 case studies. One is Beardmore Glacier. So Beardmore Glacier flows through the Transantarctic Mountains into the Ross Ice Shelf, and just before it flows over the grounding line, and then subsequently there's a sub-ice shelf channel melted into the base of the ice. This is an example where you might expect interesting glacial strain. So Twit Conway, in collaboration with Richard Hindmarsh, collected 69 P-res measurements around this channel, and combine that with all the other surveys of that channel, it's maybe one of the most well-studied such features. And then Andrew Hoffman, who was at the University of Washington when he did this work, but then subsequently now is at Lamont, analyzed these data. So this is an example. I'm going to be trying to point out the challenges with applying these systems to these places. So this is an example where, I guess its logistics essentially meant that the repeat time between the measurements was relatively short. And so what Andrew's been finding is that there's been interesting, complicated variation in the strain rates that you measure around this channel. But the signal-to-noise ratio is relatively low. So I'm not going to go into this much more, but except to say that you need to have a sufficient separation time between your measurements. So this was done with 2 weeks between the two sets of measurements, and that is kind of on the short side. So that's something which, simplistically, you have to make sure you have to kind of think about that as a challenge. Okay, I'm going to move swiftly straight onto Thwaites Glacier. So this is part of the Ghost Traverse, part of the ITGC Ghost Traverse. And Elizabeth Case, who was pictured at the bottom left, is at Lamont and soon to be at Utrecht University. She's they're a grad student here right now. So this past season managed to get 250 P-res measurements along the main trunk of Thwaites, which is shown in this map here. This is along the Thwaites Traverse. So an incredible achievement. Also, about 50 of those, they did this polarimetric measurement, which I'll tell you about. And so here is the result of those 250 measurements. And so this is not a radargram made by a profiling radar, dragged along or flown along by a plane. This is 180 kilometers of P-res measurements. This is the result of combining 250 measurements. Each one, you have to take the instrument off the sled, put it on the ground, arrange the things, connect to the thing, turn it on, do these are so-called attended measurements. So this is an incredible achievement just in itself. Now, to get what we're talking about in glacial strain, we have to go back this year. So that's super important that that happens, and ITGC and GOES, I think they have this as a high priority, so that's really exciting. So there's a challenge, right? If you're not going to do it in one season, you have to do a bunch of measurements and make sure you get back into another season, because you might be quote unquote wasting that time. So I say it's not really wasting at all, of course, because Elizabeth also did a bunch of polarimetric measurements, and so 50 of those are showing these really exciting potential variations in anisotropy. So I'm going to have to skip this because I know I'm going too slow. But what we're seeing is isotropy in the fern, and deeper there is some anisotropy. And this is really early days. But again, this is just to highlight, what I didn't highlight is that this is a huge amount of work to cover 200 kilometers. This is not the same with flying a plane. This is much, much more hard work. So that's a challenge. If you're going to be taking an instrument and taking measurements every 500 meters or a kilometer, that's a huge logistical burden. So there's another challenge. Okay, now I'm going to zoom onto the Greenland ablation zone, and this is a different kind of survey. That survey was taking many, many points along a profile. In this survey, it's a so-called unattended survey, where you leave the instrument running, ticking away for months or years, and in this case, surrounding supraglacial lakes, which have drained in the meantime. So the radar system is taking a measurement every 15 minutes. Does yellow mean running out of time? Okay, good. And this is the result. We've got time along the horizontal axis and depth along the vertical. And what we're very pleased with is you see a bunch of horizontal lines. So you're seeing layers consistently throughout the season, throughout this 3-month period. So we've got 15 months of data, 15-minute intervals, and this long list of field team members really made this happen. It was an amazing achievement to get this done. I'll skip over some kind of interesting ways to remove artifacts, which I'll be very happy to talk about with anyone. And I'll zoom in on a 3-day period, which caught my eye when I first saw this. So you may already be able to see it, but I'm going to zoom in here, 3 days, and zoom in here. I said, okay, interesting. This is the bed. It's there the whole time, and it's there after this event, but something happens at that moment. And I look back, we look through the satellite imagery, and one of the lakes drained that day. So that's really exciting. This is really early days, but clearly you're seeing something in the radar, and we're making progress towards understanding this. All right, so future plans. We've got 2 future plans coming up. One is the Crary Ice Rise. I know people have deployed APRAs at the Crary Ice Rise before, but as part of a big drilling project, led by, the US component is led by Molly Patson at Binghamton University. It's called Sways to Sea, an NSF-funded and international effort to drill through Quarry ice rise into the sediments and get hundreds of meters of sediment core. As part of that, we're making the most of that borehole and instrumenting it with a distributed temperature sensor and a distributed acoustic sensor, and we're going to do AP res around that borehole. Another one, which is just starting up, is a project which is part of a UK-US collaboration, and I'm leading the US side, which I'm happy to speak to anyone about, and it's about deploying AP res and GPS and weather stations on Flask Glacier in the Antarctic Peninsula to understand how that glacier changes its velocity in time, potentially associated with surface melting events. Okay, to summarize, it's a pretty simple message, really. These radar systems can be used to measure glacial strain in a diversity of different glacial settings, not just ice divides. The challenges include making sure your revisit times are sufficient. Covering large areas with the radar is a challenge. There's evolving surface conditions, which I didn't get to talk about. And the data ends up being very complex and large. Okay, so one thing I didn't say about the spatial coverage is that there's a whole bunch of people in ITGC who are looking at doing this from airborne systems, so that could cover that. And then just finally, to deal with this potential large complex data issue, we've been developing a Python-based package called XAPRes, which I'd be happy to talk about too. Sorry for running over. Thanks.
All right, thanks, Johnny. Next, we're going to have Merlin Ma, who's going to be talking about Alpaca, the automated lightweight portable analyzer for sea axes.
In the folder each day, yeah, so.
Okay. We can fix that.
There's a quick talk.
You're done. Everybody clap.
Any questions? There a big quiz? All right. Well, good morning, everyone. Thanks for having me here again. I'm Merlin. I'm a postdoc at the University of Minnesota, working with PI Joey Talgator. Most of you, some of you, hopefully a few of you, might remember us as those crazy engineers who keep running around trying to sell people lasers for collecting ice and drilling and cutting and all that. But we do non-laser things too, and I thought it might be high time to highlight some of that. So today, for the next 8-10 minutes, well, you thought anyone else ran over, no lasers. Instead, I want to talk about sea axes and ice fabric analysis. What a change, right? So just a very brief review for the few of you who don't know this better than I do, right? Water ice is a hexagonal crystal structure, and it's birefringent optically, which means that light travels a little faster in one direction through it than it does in the other. And so essentially, that means if you take your ice core, take a slice out of it, shave it down until it's really thin, stick it on a piece of glass. Boy, you thought getting the core itself was hard. And then you view it through crossed optical polarizers. You will see regions that are differing in brightness. You'll also see these beautiful, beautiful colors just due to thickness and interference. But it's the intensity that we really are looking at. Some areas will be black if you just happen to be staring pretty much straight down the c-axis. Other areas will have a varying sort of intensity. If you rotate it between your polarizers, that intensity will kind of change gradually. And so if you do this with all the crystals you can see in your little thin section, that's what we call them, and then you plot this, and you happen to be an experienced practitioner, knowledgeable in such things, which is not me, you can tell certain things about the ice. Like, do you have a lot of tiny randomly oriented crystals, just even spread kind of, or do you have sort of a more of a pattern? Do you have a huge just enormous crystals and a very happy researcher who comes out of the freezer in 2 minutes. Maybe the ice was warm, and so the recrystallization process, he was allowed to proceed, or maybe it was just under a lot of stress, and so it ended up kind of a random, smaller distribution. All these lovely things. This is, to date, so far, still, despite some people's best attempts, a unique, detailed crystal method for fabric data and things like the ice was and the temperature conditions at what time, and a lot of these points of data we can't get anywhere else. Now, some have tried to obviate the whole slice your preciously obtained ice core into more pieces kind of process. So this is little old me a few years back, more than I'd like to admit now. We tried a reflection backscattering technique, essentially. So stuff the entire measurement of the polarization axis process down a borehole in a gigantic instrument. And this, right now, we're trying to figure out why exactly it's not working. It's going about as well as it looks like it's going in the picture. And less said about that, the better. Essentially, we didn't test the scientific part because power issues. Fun time in my life. But as part of the process of developing this method, right, we had to sort of ground truth the technique that we were trying to prove out. So done on thin sections, how do you get the data on the thin sections that we're testing in the first place? Well, in 1958, Langway, he's the most referenced document, I think, gave us the universal stage process, which essentially is some poor researcher standing in the cold for hours and hours, tipping and tilting this 4-axis motion stage to which his or her precious piece of ice is mounted, and recording painstakingly the angle at which each crystal extinguishes, in other words, reaches extinction, that absolute black point, which sounds like a lot of fun, doesn't it? So in 1984, obviously, some people thought the same, and so they gave us essentially, okay, we can simplify the process a little bit and let an instrument help you record which angles that you're looking at, but you still got to keep your eyes on those crystals one by one by one. Don't lose track of which one you're looking at. And the time taken, they say, to measure a typical section, about 100 crystals, from a full day to between 2 and 3 hours, which, yay. But I still have frostbite. So in 2000, Larry Weiland made an important, huge step toward automating this whole thing. Well, he did it. So he used 5 motorized motion stages, 3 mounted on each other and 2, one each, to rotate the polarizers, and came up with an algorithm, basically, where you could go through rotating your sample in a fixed number of steps, a fixed number of angles, instead of tailoring your motion to each crystal to see manually hunt down that C-axis. You could actually measure a fixed set of rotations and therein figure out essentially the C-axis of each crystal. Now, 5 rotation stages, you cut it down to 4 if you accept that your sample will rotate in plane instead of rotating 2 polarizers in synchrony to each side of it. It's still a little bit much to implement. You've got to mount 3 axes on each other. It's not easy or cheap, especially if you want to, I don't know, make it small. So we came along and looked at it. We didn't have a Weiland analyzer, and so they said, okay, well, you can use one of our manual ones, and I hope you have good gloves. And being engineers and very wimpy people, we kind of said, okay, well, let's go into the rotation matrices and see if, there might be some improvement here. Now, I'm not going to go through any of these because it's 9 a.m. and no one wants to watch me do the tip and tilt axes for 20 extra minutes. But the upshot of this is, if you throw out one rotation stage and you do a bit of checking, it turns out there is an angle you can achieve with 3 stages that is exactly the geometric positioning of the Weiland stage, where it gets there with 4. And so, really, we can do some simplification, right? We can now have a algorithm that's a little bit streamlined, so that the first 3 steps are essentially kind of similar to Weiland, and the 4th one is just done using rotation or motion of 2 stages, whereas Weiland used a dedicated stage. And so if we check it out in the lab and we run, let's say this is a WDC core, essentially, thin section, courtesy of Joan Fitzpatrick. So if we run through those crystals, we get a very good error, and looks like our algorithm checks out. So, thank you. We implemented this. We had a nice hand machine, pretty much kind of instrument built, and it worked, and this is how we checked out our technique. And it was automated, but it was a little rickety. It was pretty heavy. Every time we tried to move it, the piece would fall off. And that whole project with the 6-foot-long pressure vessel really taught us, maybe robustness, portability, that kind of thing. Maybe those should be kind of priorities in our next task. So going back a few years later, we looked at this and said, well, is there anything we can do to make it smaller, make it cuter, make it rounder, cut off those unnecessary corners? Don't design for the largest thin section anyone's ever made, but just go for the most common 4-inch size. And yeah, we're calling the result the Alpaca Automated Lightweight Portable Analyzer for C-axis, hence my title. Asterisk Mark II on the right. Mark I, henceforth, never to be seen again. So, how did we kind of build this? Well, it's a few years on, so now we have 3D printers, right, are everywhere. We have this nice carbon fiber reinforced nylon that we can use very reliably, very strengthly. We can put oops, I didn't know that looped. We can put 3 inexpensive stepper motors. Interesting. Sorry, there's a addendum to that video I did not see. We can put 3 inexpensive stepper motors, 3D print essentially our own rotation stage. We can choose a box in advance, design the whole thing to fit nicely inside it to mount without penetration of the outer shell. We can take advantage of the hobbyist market and the Raspberry Pi and just put a controller right in the box and a nice webcam on an arm. And what we end up with is just a cute little, kind of a teaser here, a cute little package. Kind of the size of one of your smaller Pelican cases, less than 12 pounds, pretty robust. Just shut the lid and drop it down a flight of stairs. Please don't, or it's warranty. But essentially open the lid and go, right? So we're now designing portability first and foremost. And it can be open sourced. Its manufacturer is pretty much automated. I don't want to sound too much like one of the iPhone events or something like that, but so we're currently polishing up the hardware, getting ready to tackle the juicier task of the software. And yeah, we have a proposal pending with Margot Shaya and our own TJ Fudge here. Thank you to NSF, to our teachers, former partners, Joan Fitzpatrick and Eric Cravens, and the innovation labs that help us manufacture all this. And I will get out of here before someone tackles me. Thank you very much.
I am very interested to know how much that will end up costing. All right, so next we have Knut Christianson. He'll be talking about open polar radar software and services to standardize radar echograms, progress, and examples. Turn it over.
Thank you. So I'm going to speak this morning about an effort that has 2 principal objectives. The first is that over the last 50 years, and Dusty wrote a very nice summary paper a few years ago, the glaciology community has collected an enormous amount of radar data. That radar data is not stored in one central location, but it's spread out in many institutional archives. And the first goal of this project is to try to take that data and make it more accessible. Duncan's going to talk a bit more about this, but we're not attempting to integrate this into one giant archive, but to increase the accessibility of the data by having one central place you can look with links that will then go to the appropriate archive. The second goal of this project is to make radar data easier to use and process. And so after we talk a little bit about the structure of how we think open polar radar will work, I'll give a few examples of how it's been used and the kind of data analyses we're hoping to enable through this work. And this is a variety of institutions. That's due to the nature of the project, with many different institutions that collect radar data, and this is only a sampling of some of the more prominent ones. There are many others that do important work also. The funding for this specific project is from NSF EarthCube. However, over the many decades, NASA, NSF, AVI, BASS, COPRI, many other institutions and national programs have funded this radar data collection, and they all should be credited for their efforts. And with that, I'm going to turn it over to Duncan for the first part of the presentation. Kirsty is also one of the lead PIs in this proposal and is here as well. I was told she has too many presentations already, and thus Duncan and I should do this one.
Okay, thanks. Yeah, Duncan Young, University of Texas. Let's see. Yeah. So basically what we're trying to do, as Knut was describing, was, bring together the data products into something that is integratable, bring together the software development so we actually have code that people can mutually understand and is cross-usable and open source, and then provide a common data serving interface. So you just have to go to one place and you go to the local places. One dimension of this, of course, is that you have to make sure that institutions are recognized for what they've collected, so putting it into that context. The data coverage. So for Greenland, there's been a lot of effort. A lot of that data was collected by the University of Kansas, but there is collected over a number of years, and Kansas is an engineering shop, so there is engineering changes along the way and software changes, so that needs to be unified into a single approach. Antarctica is, everybody has their own particular radar, a bunch of different nations working in there. The coverage is getting, towards good. It's still the most poorly known piece of crust in the inner solar system at this point, but we're making progress. But there's a lot of different data sets, a lot of different vintages of data. But we have some examples here of progress that's been made, integrating BAS data and UTIC data into that common pipeline that John has been working with. The interfaces will be using an updated open polar radar based on the open polar server that John already has running at Croesus for serving the Croesus data. Right now that URL just points that direction, and at some point we will update it with the capacity to go into that interface and then point to institutional repositories, like, for example, the British Antarctic Polar Portal, which is quite robust, working on similar things at Texas. And then continue to have this package in a form that we can actually take to the field and actually do the data processing in the field. And we had some fun times at South Pole this season using that approach. So data discovery and usage, a bunch of details here, but ultimately we want to get to this fair standard of the findable, accessible, interoperable, and reusable. So making sure that you can trace things down and go from the publication to where the data is to be able to reconstruct it and make sure you can go back and reuse it as appropriately. And yeah, moving towards things like the cloud computing compatibility and Jupyter notebooks. Building up multivariant data layers, GIS compatibility. There's a project at the University of Washington looking to build in radargram accessibility into QGIS, and making sure that we have DOIs for the data products. There may be a question for the community what the appropriate granularity for the DOIs is, but and making sure that we connect to things like ORCID to make sure that recognition for the data collectors is appropriately done while making sure that the data is still usable without, contributor tax, essentially. So MATLAB and Python, we're still working towards that. Texas is working mostly on the Python front, Kansas working mostly on the MATLAB front. But the way around that is to make sure you've got good, clean interface control documents so you can go between the two appropriately. And then the other, let's see, add a virtual framing to support organization by survey grid. Again, this is differences between organizations. At Texas, we tend to organize geographically. Other institutions, just one date at a time. So a couple of examples, and I'll swatch over to the cool stuff that going to show that's relevant to the first talk of this presentation. So John has been successful in ingesting the BAS data, raw data, and running it through his full processing chain. This is a data set, I think, in West Antarctica, so relevant to WAIS. So cleanly modifying, and this, I saw this happening at South Pole. We were trying to debug some mutual issues between our systems that were flying for the Colex program, but he's able to take the raw data from Texas, run it through his processing pipeline, and get a quite nice result. You can see basal layers and all fun layers in there. Still not focused yet, but we're getting there. The hard part is often just getting the formatting down. And with that, I'll switch back to Knut. And
so one of the ways to tools in the package is for users to actually use it. And so I'm going to go through an extended example, and the ideas behind it is that we discovered a bunch of things, features that we would have liked, trying to process data in a specific way that we didn't actually know we needed. And I'd encourage you, if you're interested in this, to kind of go through and start to use the Open Polar Radar Toolbox, which is on GitLab. There's also a version on GitHub, and see what kind of tools you think should be included and come back with suggestions. And so this example here is looking towards what we call multipass data. And the idea is very similar to what Johnny talked about with the phase-sensitive radio echo sounding. We're interested in looking at strain rates. And so this is partially based off work on a proposal led by Nick Holshoe that Andrew Hoffman and John Payton and I are also involved in. And we're looking at doing interferometric processing of radar lines along Greenland in order to get at in-glacial velocities. This can be done because NASA had the foresight to fly the same lines over a 10-year period as part of Operation Icebridge when they were flying those lines ostensibly for altimetry purposes. And initially, we planned to focus on these 3 areas in Greenland where there is quite a lot of repeat data. That being Camp Century, it does buzz at you. That being Camp Century, Summit Station, and the EGIC line or K transect, which are highlighted on the left. So the interferometric processing, I'm not going to dwell on this too much, but right now we have several discrete steps, which are, it is currently implemented in the toolbox, and we're hoping through the work of Gordon Arijo, who's also involved in the project, to go to a more probabilistic approach using a joint maximum likelihood estimation of all these various steps. So when we first started this, we sort of naively thought we could do this pretty much anywhere where there were repeat profiles. And there's a lot of repeat profiles from Icebridge data. That is not the case. We found as we started to do the processing that there were very simple problems that we needed tools to examine. And so one of them, they try to fly the same repeat lines, and they do a very good job of that, but if they're not almost exact repeat lines where the wingspan of the plane is not intersecting the previous track that was flown in the previous year, we can't actually compare the radargrams to look at the phase difference between them. And so we need repeat passes, but not only that, we need repeat passes that are actually very close to each other, within 100 meters. And that was not something that was easy to search for in an automated way in the Croesus toolbox or in the Operation Icebridge data portal. And so Nick wrote tools to do that. And as you can see on the map on the right here, that took the lines that had repeat profiles down from quite a bit of the ice sheet to these lines that are in the blue here, which is still extensive but much smaller. The other thing we need to know certain things about what the radar instrument was. And so in this case, we need to know about what kind of radar antennas were used, what the array setup was, what the platform it was flown on was. And that's not easy to search in the current databases. And so to dive beyond the direct imaging problem into something that's more, that maybe is a bit more sophisticated but fully utilizes the data, you need this additional information, and there weren't software tools to do it, so we had to build our own. And this is one of the examples for Camp Century, where we look at that. And Camp Century is flown all the time because they operate in and out of Thule. And so there are hundreds of total repeats. We found 49 that were appropriate that we could use. And then they span a number of years, and so we can start to do comparisons. And so just to show the example of where this actually gets to, this is a line outside of Summit. And when we could actually find data that worked well, where it was close enough together, where there was a multi-element array, so we could estimate what the effects of cross-track slopes on the interferograms were, we can map out what you see on the top here, which is still a messy, but moving towards a result of profiling using airborne radar data. And that profile is about 30-kilometer section near Summit. It's not oriented in any interesting glaciological way, but it's a proof of concept of what we could do if you had proper tools and what everybody could do with the existing archives. The graph on the right shows just as a comparison to, these are actually PRES data that were taken nearby And we can kind of see that we actually have a neater clustering from the airborne data, but it's very sensitive to exactly where we choose and how we average in order to make these vertical velocity profiles. But it's encouraging, and these are the kinds of efforts we hope Open Polar Radar will enable for the community. And I'd encourage you to, we are still very early in this project, and so I'd encourage you to go look at Open Polar Radar, and it's still at a preliminary stage, but we are happy to take suggestions about what kind of data sets might be missing or should be included, what kind of queries people want. I mentioned we needed geographic queries, we needed radar system information queries, things that were not in the previous tools, and what kind of processing you're interested in. So I showed one interferometric processing that ties into more commonly used PRES, but there's also other radar techniques for a variety of purposes, polarimetry and swath mapping being two of the other most prominent new techniques. We're hoping to run workshops in summer 2024. One of them will be a dedicated workshop. There'll be like a hackathon for a week, we hope, and there might be a number of short courses and afternoons attached to meetings like this one. And I think I'll stop there. I'm already over time, so thank you.
All right, thank you for that tag team presentation. Next, we're going to have the discussion, so if each of the speakers can come to the front. Online users can be using Slido to ask questions right now. For the discussion, I want to remind everybody, I really want to invite early career researchers to be asking questions and participating. We want everyone to participate here, and everyone is welcome. And to make sure I don't miss anything. We're looking especially to draw connections between the talks and the directions that we want in our community, so definitely ask questions in that direction. And I will turn that over for you to start questions.
All right. Is there one more slide? Yeah. Yeah? Ah, all right. So as, and what do I need to do to bring it up? F5? Just. No? Let me go to the last one.
What was it? First day, morning, we're all waking up.
There you go. Great. Thanks, Knut. Bob Jacobel. I'm emeritus. I'm retired from St. Olaf College. Done lots of radar. As one of the senior people here, I thought just take a second to give you some perspective on the talks that you've just heard. Yeah, this is, a lot of people have noted that glaciology has moved from a data-poor science to a data-rich science. And you've had good examples of that in the last three talks where we're talking about terabytes, even exabytes of data. This is an image that was taken up on South Cascade in 1984. And I realized in thinking about that, probably half the people here or more weren't even born in 1984. But this is the beginnings of radar on a temperate glacier. There had been airborne radar had been flown in the 50s, but temperate radar was a bit more difficult because of the scattering, and so you needed longer antennas. So this is an oscilloscope, battery operated inside of a backpack, and the data were acquired with a Polaroid camera. And you'd pick this system up and you'd move it from one place to the next each time, take a picture. A picture gives one data point, 2 bytes, basically, a depth. So from the Polaroid picture, you can measure the time, and from the time you get a depth, and that's one depth measurement. So we've come a long way, is the point. So I think just with that introduction, open it up for questions for the speakers. Go for it. There are microphones, yeah. One over here, one over here.
All right. Yeah, thank you for all of your guys' talks. I was really interested to know, like big picture, where you think the most important measurements are to still be taken for each of your instruments and data and things like that to kind of go forward and kind of learn the most that we can about WAIS.
I mean, it's obvious. Something which isn't completely my field, but much more in what Knut and Duncan were talking about. Obviously, there's still big gaps in our coverage of both continents, right? I mean, places we don't know how thick the ice is. That's a clear, important thing. And I guess just specifically about in-glacial strain rates, I think you speak to people who might incorporate those data into models, and they ask for as close to the grounding line as possible. And for example, the ghost traverse is limited in how close it can get to the grounding line because of just hazards, just because of crevassing. So if there's systems like the ones you're talking about, like the approaches you're talking about, the glacial strain rates from the air, if you can somehow get around the issues with crevassing on the surface near the grounding line, which you're going to face, then those areas are going to be really crucial for people testing out their models in the way I was talking about, the grounding line and the region immediately upstream.
So historically, I think we've done this by plugging gaps, either where we can't get ground coverage or where there's gaps in the data. And for the radar systems in the airborne, we've also historically flown gridded patterns. And I think we need to think more carefully about what the objectives are we're trying to measure. And so gridded patterns might not always be best. And so, for example, Thomas, who's working with Dusty, has a presentation later this conference where he's going to talk about how if you did have in-glacial vertical velocities, either from a profile such as the one Elizabeth collected or the ones we're trying to construct in Greenland, how you could actually use those profiles integrated into modeling in order to come up with a 3D velocity field when your data set, despite being so rich, is still sparse compared to what you're trying to understand. And I think thinking through processes like that are closer data model integration is important for guiding how we do these types of large-scale surveys. And so in this case, the obvious answer might be flow lines, but it's sometimes not necessarily that simple. And so flow lines over interesting areas, as Johnny suggested, and then trying to make sure that we have active conversation with groups that are working on how you might apply these data if we're not doing it ourselves.
Yeah, an example of that is actually from the Kingslake surveys we're doing up in East Antarctica, where we have actually made a compromise, a grid that is oriented around the flow lines coming off Dome A. TJ's happy about that. So one thing, a message to NSF and reviewers, we've got lots of coverage up there, but there's a lot of different vintages. So just because we've got coverage represented on the bed map doesn't mean that we shouldn't go there again. Some of the older data is we were still learning radar. We're getting better. We've still got a lot to learn. But there's also, from things like the repeat interferometry and other approaches, things to learn from revisiting these lines down the track as we've been observing Antarctica long enough that, you know, it's starting to change over the course, even in the interior. So that's just a message to review panels.
So I saw Sridhar's hand.
Bob, if you could put your picture back up again.
I probably can't, no.
Well, my point is that, Bob is from a smaller school, and there's lots of other folks who are not perhaps at University of Texas, University of Washington, or Columbia University, and the technology that you used was an oscilloscope and Polaroid, and was very successful at that. My challenge to the radar community is to bring and generate and make a radar that is really open for everybody to use. And I think you're headed in that direction in the software, but I think the hardware is still expensive and difficult for a lot of folks to access, and it should not be that way. We have come so far in the technology, and I really, do you think we're there where somebody can kind of for $1,000 there in Glacier world doing other projects?
Can you take that one?
I can start and then somebody else can follow on. I think it depends on the objective. The multi-element arrays, the kind that Croesus has historically flown, the kind that Texas flies, still require a lot of engineering, electrical engineering know-how to apply well in the field. And however, I think there is a parallel effort to open polar radar that Seth Campbell and Zoe Corville have led, and they've had a series, I think they've had 1 or 2 workshops now on how to make exactly what form it takes is unclear, but how to make a radar instrument center that's analogous to what is from IRIS Pascal or from UNAVCO, I guess EarthScope now, that they're combined. And I think that is feasible. And there's also a number of commercial options or semi-commercial options that are significantly more advanced than they used to be, including things that can now begin to do frequency chirps. And if as a community we can buy a few of those instruments, say half a dozen, that would be something that could become more accessible. We're still maybe, I think, in terms of if you were to take the types of radars Croesus builds, that's still kind of I would say a 10-year perspective to get those into something that's easy for everyone to use. But the type of radars that Bob's worked, I'm not an electrical engineer, and we've been able to replicate those for a few tens of thousands and can successfully sound dice for geometry and layers. And one of the things the toolbox might enable is we might be able to do some more advanced analyses even on those data. They're not phase sensitive, but they have a good phase signal. It doesn't vary too much, and you can do some things like look at how reflectors change in phase. It's not the same thing as polarimetry, but you get some useful information out of it. So it depends on what you want to do with the radar data, a little bit about what instrument you might want to use. One last note is there are now things that drone radars are available commercially, and if we bought a couple of those, you could start to use those to map hazardous areas as well. And they're, again, impulse radars, so they're relatively simple systems conceptually, but that's not necessarily a weakness.
Christy?
Is this on? Button. Oh, it was on. Maybe I just need to get really close to it. Does that work? Yeah. All right. You probably know my question. So you guys mainly spoke about deep sounding radars. Are you considering including more shallow radar? Because there's lots of interest in vertical strain in the fern as well. And so I think we're trying to kind of work on that with the Croesus snow radar, and it would be a really awesome addition to your guys' work. So just thoughts on the shallow component as well.
Yeah, I mean, that's a great point. I think you may already be familiar with the work, but for other people, Elizabeth Case also wrote a paper about using both types of radar, P-res and AP-res, to get strain rates in the fern. And there's some limitations because the antenna and the whole system's a little bit big. So you can't really look at things within the top 10 meters. So scaling that system down to smaller wavelengths is definitely a good effort. But we did get useful information out of the existing systems for that exact area you're talking about. So absolutely, I totally agree. Yeah.
So these toolbox tools are designed to work with the full range of Croesus radars, and so they ought to work with the snow radar. I don't know if any of us have actually attempted that, but the 2 to 8 gigahertz standard radar they deployed, it should be possible. However, this is another collection question because sometimes that radar is prioritized, other times it is not. And so sometimes when there are years in Greenland, for example, when they didn't fly with that radar when they were using the C-130 as a platform. And so when we're thinking about how to plan these missions, that's a factor if we're trying to use a variety of radars.
Thanks, everyone. You gave really exciting talks. My question, I guess a few people could answer, but is about power interpretations in open polar radar, and if you envision any issues coming up with that. Winnie Chu wrote a great paper a couple years ago where she kind of matched the bed echo power from the Bassin data and the Agassi data at weights, and hopefully that type of analysis could be a lot easier and within a framework like open polar radar. I don't know if you've thought a lot about what the problems might be in doing those types of analyses as we're integrating across systems.
I know that was explicitly part of the proposal, was to get into the radiometric side of things and look at things at intersections as well as reef lights and try and figure out what is going on there. But often there is a lot of issues there. We're looking at, making sure you've got the full dynamic range of the system in your processing.
So I guess this is a follow-on to both Sridhar's question about the affordable radar and then also the attempts to make these portable sensors for the fabric. So there are systems, and you can talk to Thomas, my student, later about this, that are being presented that are, sort of single-digit thousands of dollars drone radar systems. Also, my student Anna, who's not here, but Thomas can represent, has a ground-based chirped software-defined radar, and my former student Nicole has a biostatic system. These things all come in at the price point that was being asked for. So I think the question for y'all is, other than giving talks like this at conferences like this saying these things exist, what is the way that these things that are going to be presented and published in an open source sort of way should be brought into the awareness of the community so that the answer to that question is well known and people feel like that's something that's accessible to them?
I can give an attempt to answer that, and I think it's that we should team up with more efforts like what Seth and Zoe are doing, where they're trying to make this an explicit objective of that workshop. And ours is more geared towards the software development and data use side, but gathering that data is equally important to making sure people can gather data they need for those purposes, and then making sure that we survey the full range of different radar systems that might be of use to the community and what people actually want. The funding mechanisms for that are something we also need to think about as a community. And there have been different ideas thrown around for how we could fund a startup instrument center, and it in some ways is easier to get the initial money that you get to start it than it is to make sure that it's a sustainable center after that, where these radars are looked after and where there's it might not be exactly the same model as UNAVCO and Pascal or EarthScope have operated under, but some group that can both make sure the radars are looked after and that they are maintained and that they advance with the capabilities of the technology, and also that there's a way to make sure that there is a pathway to access those radars. And so I think we should learn from those centers, but we're early in the process. Initial ideas for funding the startup costs to get the instrument center going have been a mid-scale infrastructure award, and so that has been investigated. But I'm not sure that's not the complete answer for the longevity of the program, making sure it's sustainable throughout.
Yeah, I think it's a great question. I don't have really any experience in getting a technology out to a community before, but one thing I've been getting excited about is the software for the radar or the AP res processing stuff. So that thing I just had a brief mention of at the end is something I've got really into, of using tools like CryoCloud, which Tasha's going to do a workshop at the end. So those kinds of tools where to deal with tens of gigabytes or more of data in a completely open source way. I mean, at least give people the tools to process the data with these instruments that they ideally get hold of. I agree your question really is about how do you get these out to people, but the thing I've focused on is the software, and I think that's also a pretty good effort. Also, there's educational aspects to this. So you can, we've been working on a so-called Jupyter book about glaciology generally, but there's chapters on phase-sensitive radar processing. And then another one is the Juno Icefield Research Program. It's a great place to educate the next generation of cryospheric scientists, and bringing in AP res, which is one of those radars I was talking about, is a very good way to run a field class up there, and it's very lightweight, and it's a great fun trip. I recommend everybody looks at it and tries to write it into their proposals.
We have time for one more? We'll have one more.
Hi, I had a quick question for Duncan Knut in particular. I know things like Open Ice Bridge have similar open radar sort of initiatives. Are you planning on integrating those two with Open Polar, or is there like a difference between the two that you're distinguishing?
IceBridge, a lot of the data sets that were collected for IceBridge are part of the Open Polar Radar effort. Kansas collected a lot of it, and also Texas collected a lot of that data. So it was made available through NASA, through various NASA processes and expectations for data release through the NSIDC. There are also parallel releases of many of that data. And so with the that's one of the things we're going to have to reconcile with the Open Polar Radar effort, is that in many ways this data has already been released with a particular set of processing, which the careful user needs to be aware of, compared to the data that's available in other forms. So whether you use a single DOI or multiple DOIs for those different data collections, which have been processed different ways, is a kind of a unique issue with radar data in terms of how many ways you can scramble the photons. Yeah.
Is it good? Are we ready to go to break? Okay.
Yeah, so we're going to do a quick introduction to people that have posters. So if you submitted a slide associated with your poster, please come up front. You have about a minute to talk about your poster. If you have a poster and you didn't submit a slide, please feel free to come up here, or we encourage you to come up here and just give us sort of a 1-minute overview of what you're going to be talking about as well. It'd be good if you could just state your name, where you're at, in addition to what you're talking about. The posters are already up. They're behind us. There's a large room. Yeah, yeah, not all. All right, 3 hours is not up. Yeah. Right. So here's the test. You have to arrange yourself alphabetically. So, yeah, yeah, by your last name. Yeah.
I doubt mine will be up there because I.
Yeah, it should be. Yeah. Okay. All right. Okay, that's fine. If you wait till the end. Yep. 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 Yeah, so maybe arrange yourself to my left, your right if you're looking at it alphabetically. Yep. If you didn't submit a slide but you still want to talk, which we encourage, maybe come after the people that have put slides, so that we just roll through the slides first. This morning-ish, yeah. Okay, we're getting close here. Okay, all right. Well, I think we're getting close, so I'm gonna let Julia take over first. So if I could get people's attention here as we sort this out. Are you ready? Okay, go ahead.
Hi, everyone. My name is Julia Andreasen, and my poster is titled Assessing West Antarctic Ice Rise Climatology and Ice Core Site Suitability Using Reanalysis and Back Trajectory Analyses. So basically, we're looking at 12 ice rises along the coast of the West Antarctic ice sheet, and we're breaking them up into the west sector and the east sector, and trying to understand what the climatology is for each of these locations. First, I did a bit of a high-split back trajectory analysis, so basically understanding what the precipitation pathway is for each of these ice rises and how they differ from the east to the west. And then also looking at the reanalysis data sets for each of these ice rises. So how does their precipitation rate change, and how does their temperature change? And then from there, we kind of were able to confirm this dipole that was defined by Medley and Thomas from 2019, as well as sort of understand better where we want to get our ice cores, which will also be talked about at Peter Neff's presentation on Wednesday, I think. So yeah, feel free to check it out. Thanks.
Hi, I'm Louise Borthwick. I'm at Temple University, and I'm presenting some data that we collected in Antarctica this past season near the Waste Divide camp up at the top end of Thwaites Glacier. And it's basically some seismic and gravity data, and we're using it to try and look at upper crustal structures, see what's immediately beneath the ice. So I have a model that I've created based on the gravity and the seismic data, using open source Python tools to model the gravity data and ray tracing tools for the seismic data. So if you want to talk about any of those things or upper crustal structures, come check out the poster.
Paranoid, I'm going to spill this on the computer. I'm Brooke, University of Wisconsin, and my poster is about indicating the influence of friction, basal slip laws. So slip laws are really important because if you want to predict sea level rise over the coming centuries in Antarctica, then you need to know the slip law at the base of the glacier in those fast-flowing regions of ice flow. And if you look at the figure on the right above these great poster presenters, you'll see that there's a huge variety of slip laws that people have proposed. So the most common is that Weirtman-style power law. That's most commonly implemented, but there's also plenty of other ones that show kind of like a rate-independent behavior past a certain slip velocity, or even a double-valued relationship where there's some rate weakening as you reach higher slip velocities. The shear stress actually decreases. However, all of these slip laws assume that the only source of drag at the base of the glacier is due to flow around obstacles as ice has to squeeze and stretch around it. But in reality, if you see the figure on the left, the base of a glacier is really dirty and there's lots of debris. So an additional source of friction would be that debris pressed up against the surface of bedrock obstacles. And that hasn't really been studied too much. So basically what my poster is, which you can see later, is using a numerical ice flow model to do some idealized simulations of slip, and then figuring out how debris bed friction affects the form of that slip law.
Okay, I'm Roger Buck from Lamont Doherty, and we're breaking all rules of PowerPoint, putting too much on a slide here, but it's because we're talking about two theoretical problems driven by different observational sets. One of them asks the question, driven by observations of rifting in areas of moderate buttressing. We ask the question, how does it happen? And we point to meltwater having a big effect and being able to drive rifting. The second problem is about bending on a short wavelength at the end of ice shelves, and there's only one model been published about benches pushing up the end. We have a different model, so come see that.
Hi, I'm Mike Cloutier at the University of Minnesota's Polar Geospatial Center, and my poster is going to highlight the improvements to the second version of the reference elevation model of Antarctica. In 2017, we did the first version that was released, and last October, the second version came out with a number of improvements. Most importantly, it expanded the temporal range of the data an additional 5 years up to late 2022, introduced some new mosaicing methodology, improved ocean flattening, and included some Southern Ocean and subantarctic islands that the previous version did not include. So looking forward to discussing it with anybody who would like. Thanks.
Hi, my name is Nia Duncan. I'm a senior at Binghamton University, and my poster is on the late Miocene to Pliocene lithostratigraphic changes at IODP site U1522 in the Ross Sea. It's supposed to be a poster teaser, but I accidentally uploaded my whole poster. But mainly in order to answer the question of what's actually going on down core, we are going to be examining we're going to be doing a high resolution X-ray diffraction on the core. And then in addition, we're doing a cluster analysis in order to kind of compare what the mineralogy is telling us to actually what's going on in the core. And then to kind of tie it all together, we're also doing XRF analysis in order to kind of see what's going on during these like interglacial periods. But yeah, come and see my poster. Thank you.
My name is Brendan Eckerman. I'm an undergraduate meteorology student at the Metropolitan State University of Denver, and as part of an undergraduate research experience this past summer, I did an examination of surface melt-inducing atmospheric rivers over the Antarctic Peninsula. So basically what I did is took a bunch of satellite data and compiled a bunch of surface melt events across the Larsen Sea, and then figured out if there was an atmospheric river that passed through within 24 hours, and then kind of classified a little bit of the general meteorological conditions that were associated with that atmospheric river that passed through and caused a surface melt event. And yeah, that was pretty much it. Come check out my poster. I'm Michael Field. I'm from the University of Florida. My poster is about improving estimates of sub-ice shelf bathymetry in Western Antarctica. So I invert airborne gravity data constrained by multi-beam echo sounding offshore and radar inland. But the important thing is that I use a Markov chain Monte Carlo stochastic optimization approach. So I'm actually solving for the full posterior distribution of the bed. So this means that I have a 2D spatial map of the uncertainty. Yeah, thanks.
Hi everyone, my name is Heather Furlong. I'm at Northern Illinois University, and this is the culmination of my master's work. So it's the link between iceberg melt and diatom productivity, demonstrated through analysis of mid-Pliocene Amazon Sea interglacial sediments. That's a mouthful. So I was looking at sediments that came from IODP Expedition 379 to see if we could find correlation between icebergs and diatom primary productivity. Spoiler alert, we did. So if you want to learn more about marine diatoms and how that happened, come to my poster.
Hi, my name is Danielle Grau. I'm a third-year PhD student at Georgia Tech, and I didn't submit a slide, but my poster is mainly analyzing surface roughness of Antarctica and how we can use quantifying surface roughness to predict mean aerial and mean superglacial melt lakes. Yeah.
Hi, I'm Veronica, and I'm at Cornell. My project is using the ROV IceFin to look at the water column properties and ice ocean interactions between Erebus Glacier Tongue and McMurdo Sound. So looking at the temperature, salinity, and oxygen, we saw that there is mixing of three different water masses, glacial meltwater, high salinity shelf water, and Antarctic summer water. We also have a vertical profile from near the grounding line where we see that there is a flow of meltwater out towards the open ocean. And then finally, the ice base changes drastically at different locations, and this indicates that there are likely different melt rates and melt modes at different spots beneath the glacier.
Hi, my name's Andrew Hoffman. I work at Lamont Doherty Earth Observatory. And today I'm going to be presenting two observations, but this work is done in collaboration with many people, including all the folks who collected data as part of the Rosetta project, and then field efforts that happened in 2013 and 2014 to collect HF radar profiles across the Beardmore grounding zone. So we identify a melt channel that forms at the Beardmore grounding zone, and then the poster presentation will be about kind of how this relates to some basal bodies that we observed downstream in the Rosetta data. Thank you.
This one, right? Yeah. Okay. Hi, I'm Susan Howard, and I'm at Earth and Space Research. Lori Padman and I are using ISAT-2 with WorldView DEM, SAR, and MODIS to look at grounded icebergs along the East Antarctic coast. We can measure the elevation of the icebergs, and from that we can get the draft and then estimate the water depth, which is great in areas which have little actual measurements. And we're also interested in the interactions with landfast ice. So I'd love to talk to you about this at my poster, and we're also really interested in meeting people that are interested in doing SAR image tracking and WorldView DM processing. So come and talk to me at my poster. Thanks.
Hi, everyone. Yeah, my name's Sam Kadam. I'm a third year at UC Santa Cruz. And I'm looking at the role of glacial isostatic adjustment in raw sea deglaciation. There's questions of what's the role in GIA in like future grounding line shifting, raw sea, Holocene grounding line shifting. And I'm just kind of taking a step back, big picture approach. What's the whole deglacial role of GIA? So this figure, the green area, that's the interior of the raw sea that's been uplifting, sea level fall over the deglaciation. The brown area that's been subsiding or sea level rise over deglaciation. And for a good part of the beginning of deglaciation, the grounding line's out on that area where you're subsiding, or you're having a relative sea level rise. So there's kind of a, throughout the deglaciation, the role of GIA in grounding line retreat is going to change. Right at the beginning, it's kind of contributing to grounding line retreat, and then as you kind of enter that uplifting zone, it starts to be more of a stabilizing factor. Oh, and if you are an ocean circulation person, please come talk to me.
Hello everyone, my name is Caitlin Locke and I am a third year PhD student at Lamont Doherty Earth Observatory of Columbia University working with Christianson, and the title of my poster is the Onshore-Offshore Geologic Investigation of the Amundsen Sea Embayment. And in the Amundsen Sea Embayment, understanding the ocean ice and earth ice interactions, including the geologic environment, are important for improving our knowledge of future projections of Antarctic ice sheet stability and sea level rise. And for this work, we began by focusing on the offshore environment by compiling available seismic, gravity, and magnetic data in order to understand the geophysical signature of the basement and what shallow and deep signals are present in the potential fields data. And for my poster, I focus on 3 of these seismic lines, so please come visit if you want to learn more. And in the future, we plan to expand this analysis to additional offshore data and onshore data. Thank you.
My name is Lynn Kajuzinski, and I am a representative for the U.S. SCAR, so the Scientific Committee on Antarctic Research. If you don't know what that is, please come to this poster. We are trying to build a network of Antarctic scientists here and use that as a stepping stone for international collaboration with SCAR International. We're also building a directory so that people can look up other scientists that might have the same discipline, work with the same data, working in the same area of Antarctica in general. So definitely come by and sign up for the directory if that's something you would be interested in. I'm also presenting on some of my work in Alaska on the impacts of tidewater glacier advance on iceberg habitat. So I'm looking at impacts on harbor seals at Johns Hopkins Glacier in Glacier Bay National Park. So we're looking at this interesting record from 2007 to present, where we can do an iceberg segmentation algorithm. So we're looking at iceberg concentrations over time and how this advancing glacier is impacting that, and then how that's impacting seals. And then we're also looking at short-term implications. So we set out time-lapse cameras and use that and tracking icebergs to come up with circulation models of surface flow, and then comparing that with where seals are in the fjord. So come check that out. Thanks.
Keep going. One more. Yeah. Okay, hi everyone. My name is Michelle McLennan, and I'm a 4th-year PhD student at the University of Colorado. And I am going to be presenting on every glaciologist's favorite topic, the atmosphere. So we've done a lot of work in the past 4 years to look at how atmospheric rivers impact the surface mass balance of Antarctica. And we found that despite their rarity, atmospheric rivers bring a ton of snowfall and melt to the Antarctic ice sheet. In particular, they drive large interannual variability in the total amount of snowfall, and they can also impact the stability of Antarctic ice shelves. So that's what we know about atmospheric rivers, but we really don't know yet how they might change in a warming climate. And so that's what I'm working on right now. So if you're interested in this, come by my poster.
we're looking at how atmospheric river frequencies and intensities might change by the end of the 21st century as a driver of changes in the total amount of moisture in the atmosphere and also changes in the large-scale circulation. So if you're interested, come by, let's talk about the atmosphere, let's talk about surface mass balance. Thanks.
Hi everyone, my name is Natasha. I'm a third-year PhD student at Wisconsin-Madison with Luke. I'm studying subglacial mechanics, specifically focused around grounding line pressure oscillations. We do this by using a large diameter cryogenic ring shear device, which is on the left, to simulate a variety of conditions, including the period of the oscillations, the amplitude, and then also the till type. So I'm specifically looking at how these pressure oscillations will affect the drag response and the general hysteresis within the system, which means the time it takes for the system to respond to those applied forces. So if you'd like to talk about that, please come by my poster. Hi everyone, my name is Rachel Miney, and I am a master's student. I'm really excited to some work that I've been on called Colgate University. I'm studying ice-ocean interactions at the outlet of the Totten Glacier, which is in East Antarctica. Y'all might be wondering why I'm presenting stuff from East Antarctica when this is clearly a conference about the West. But as you can learn about it in my poster, it's subject to similar thermal forcing as parts of East Antarctica is grounded below sea level. What I'm contributing is the diatom assemblage record from an ice proximal sediment core from the Sabrina coast. And I've shown up on here some of the preliminary units that we've broken it down to study the ice-ocean interactions from deglacial to present.
Hi everyone, my name is Gavin Piccioni, and I'm a postdoc at Brown University. And in my poster, I'm going to be presenting on some of our measurements from a subglacial precipitate, which is a rock sample I'm showing here on your left. These samples form in water at the base of the Antarctic ice sheet, and so I'm interested in using them as archives of subglacial water chemistry. In this project, we dated this rock sample and showed that it is forming across termination 3. That's the curve in the middle. And did some elemental analyses, an example of which I'm showing on the right. And we're showing that after the termination, we saw a large spike in redox-sensitive elements. So the key takeaway of this project is going to be that climate change across terminations can regulate subglacial trace element mobility. So if you want to hear more, come by my poster. Thanks.
Hi, my name is Chancellor Roberts. I'm coming from Scripps Oceanography. Ice shelf rift growth and propagation culminating in the calving of tabular icebergs accounts for about half of the mass loss from the Antarctic ice shelves. However, the role of melange in these processes still remains poorly understood. As such, we've been using ICESat-2 to isolate the melange elevations and then characterize their surface roughness to look for seasonal variations. And we find some pretty interesting changes in the root mean square error of the elevation on Filchner ice shelf. So come take a look.
Hi everyone, I'm Becky Sanderson and I'm one of the few people from the UK here. I'm based at Newcastle Uni. So I've been using the PASSIN data and the PASSIN-2 data to trace internal layers across Central East Antarctica, linking up the South Pole with Dome A, which then now extends the database of traced internal layers right the way across to Dome C, which you can see in the bottom figure down there. We have been kind of looking beyond this and looking at why there is a bit of a drawdown in internal layers at the South Pole and what this may mean for past ice dynamics or geothermal heat flux. But we've also been looking at potentially where the oldest ice is in the region by using our deepest layer as a proxy for old ice at the bed. This significantly contributes to the SCAR action group Antarchitecture. And yeah, this is East Antarctica, but I'm hopefully providing some of the necessary links to then connect further into West Antarctica. Thank you.
Hi everyone, I'm Nicolas Sartor. I'm coming from Wisconsin-Madison University, and I'm trying to figure out if ice shelf may have a flute. And in more scientific terms, I'm trying to investigate how wave may impact ice shelf, trigger deformation, and even calving. So if you want to talk about Ross ice shelf, ice altitude measurements, ice beam deformation, please come talk to my poster. I would be happy to discuss that. Yeah, I try to use simple blade to investigate ice shelf fronts. Thank you.
Sorry, I didn't get in line. Oh, there we go. This is not my poster. This is Elna Savage, who's a PhD student in our group's poster. But she couldn't come, so I hung it up, and I'm the one that'll be standing there maybe. If not, Tasha will probably be around to talk to you about this. But we all love Pine Island Glacier in this room, I think. And there's some really cool polynyas right at the front that a lot of people have worked on, going all the way back to Bob Binshadler 15 years ago. And what Elna did was finally compile the time history of these polynyas for the past 20 years using MODIS imagery and Landsat imagery. And so we have this beautiful time series of these polynyas. These polynyas show up most years, get as big as 300 square kilometers. And so these are, wintertime massive interactions between the atmosphere, the ice, and the ocean. So come talk to that. Come talk to me at that poster. I'm also going to tell all the students that are up here to make sure to pin the QR code to your poster so everyone can give you feedback. Thank you.
Hi, my name is Megan Sharp. I'm a second-year PhD student at Oregon State University. And so if you're interested in 5 parallel rifts across the Thwaites Eastern Ice Shelf, come check out my poster. I'll be mostly showing a synthesis of work done with and largely by my long list of co-authors. We'll be showing patterns of the rift growth, radar profiles across the rifts, and then largely a lot of questions about the actual drivers and mechanisms of these rifts and putting them into potentially some context of the larger Thwaites Eastern Ice Shelf system and recent calving events.
Hi everyone, I'm Tasha Snow and I'm a researcher at the Colorado School of Mines. Kind of piggybacking on what Matt just talked about, the work that I'm going to show is looking at persistent polynyas. Also at Pine Island, these are caused by plumes that rise to the surface. They're driven by basal melt, subglacial discharge that are buoyant and often come to the surface and carry residual heat. So we can observe them from satellite. So this work uses ISAT-2 data that is created by Slide Rule from Susan Howard and Lori Padman. And we pair that with thermal imagery from Landsat. Some of that's been processed with an algorithm we've built to create sea surface temperatures. And we're looking at the structures of these plumes and the polynyas over time. For a lot of this work, we're also using state-of-the-art deep learning algorithm to do surface identification, and using a lot of open source software and CryoCloud. So if you want to talk about any of those things, please stop by my poster.
Good morning. My name is Val Stanley. I'm the Antarctic Core Curator at Oregon State University's Marine and Geology Repository, where we house over 24 miles of mud from around the world. Roughly half of that is from the Southern Ocean. So yeah, who here has worked with marine sediment samples or data derived from them? Fantastic, great. You and everyone else are invited to come visit my poster, and we can chit-chat about our collections, our instrumentation, our services, as well as the work that we're doing over the next 5 years to kind of make our data products and our samples a part of the FAIR data ecosystem. And I'd also love to talk to you about citing your samples in your publications. It's something I'm very passionate about. So yeah, thanks.
Hi, I'm McKenna Zemak. I'm a first-year PhD student at Texas A&M Corpus Christi. This is my master's work, and I use the cores Val just talked about to look at the Amundsen Sea polynya and some interactions there. This is the best figure I've ever seen to show this work, or show this system. So there's no dense shelf water, so you get increased circumpolar deep water inflow. And because polynyas are really productive environments, we can look at this system. So I looked at 10 cores across the shelf and counted a lot of diatoms. And I found 4 main paleo-environmental units. And that's just an example of 2 of my cores. You can see those units.
and see how the piston cores and the trigger cores don't really line up. So to talk about what those units are and why they don't line up, you can come see my poster and all my really pretty diatom pictures. Thank you.
Hello, I'm Kirsty Dinto, and this poster is from the USAP DC. The most important thing is the website address in the middle there. If you have recently been encouraged that there's a lot of discovery to be made in data reuse, you might be interested in the search functions on that website. If you have recently been awarded a grant to make some discoveries, you might want to register your project with us. You do want to. And you can also deposit data sets. We collect together data sets from projects wherever they are archived, so it's a one-stop shop that's in close connection with those other data archives that you've heard from. Thanks. Oh, and we're having a workshop on Thursday afternoon after lunch where if you have really in-depth questions, you can come and get them all answered.
Hello everyone, my name is Kira Duran. I am a second-year PhD student from Georgia Institute of Technology. So my research is focused on ice-ocean interactions and also ice shelf basal observation using airborne radar. And the poster that I will be presenting will focus on the projects that I have been doing for the past 2 years since my undergrad. I will be presenting a new map of Ross ice shelf basal melt rate, which derived from the attenuation laws. That is dominantly controlled by the temperatures. So if you want to know more detail, please come by my poster. And I would like to thank NASA and NSF for the opportunity. Thank you.
Hi, I'm Sarah Vilhauer. Is that on? Okay. I'm at UCLA, but this project started at OSU. My poster is on ocean-driven melting near and within ice shelf basal channels and crevasses. We ran large eddy simulations of ocean circulation within basal geometries, so we can look into how this circulation influences melt and the evolution of these morphologies. Across our simulations, we varied 5 parameters, so channel width, far field temperature, salinity, velocity, and the orientation of that velocity. So we can calculate sensitivities of melt to each control parameter, and the ultimate goal is to use non-dimensionalized momentum and thermal forcing to predict melt rates across a wide range of conditions. Thank you.
Hi, I'm Julia Wellner. I'm from the University of Houston, and I'm presenting some data that has been compiled by many of my students, some of which has been presented here in pieces in the past, but none of my students were able to attend this year. And we are part of the Thor collaboration. And if you go to the poster, all of us are listed individually there, but there's a long list of these authors. So as part of Thor, we have had several field seasons offshore of Thwaites, but also Pine Island, and now more recently Dotson and Getz. And what I work on is the marine sediment cores, like Val mentioned. Our cores are stored at Oregon State. And come to the poster if you're interested in the details, but my broad message for you is that using these sediment cores, we can record changes in the Thwaites and Pine Island glaciers, not just over the Holocene or the last several thousand years, but also over the last 100 to 150 years. We can monitor changes in the ice and ocean. Thank you.
Hi everyone, my name is Caroline Wexler. I'm a senior undergrad at the University of Connecticut, but this summer I was working with Coldex at the University of California, Irvine with Eric Saltzman, and what we've been doing is trying to understand the relationship between fire and climate, especially with rapid climate change now. So what we're doing is taking ice cores and taking methane and acetylene trace gases in those ice cores to try and reconstruct fire events. And one of the students was looking at it in the past millennia while I was looking at it during DO8. And what we found was this interesting difference between the two fire proxies.
So come to my poster to learn more about that. Thank you.
Do you find it ridiculous that it's 2023 and we don't understand how ice melts in seawater? Because I do. And I decided to throw some GPUs at this problem, and I would love to show you some of the results. Yeah, it's a pathological problem with interesting results.
So actually, well, I guess I'm pretty too serious actually in animation of this, and so I'll just shut up, okay? So there are actually really two aspects of my poster. One actually is really try to understand better about the, observe the GPS observation of the crust motion in Antarctic. And so there, as we know, this is 1D models that actually suggest very, very small viscosity for the upper mantle. So what actually we're looking into here is really we want to look at a more realistic mantle viscosity, including 3D and non-Newtonian and possibly transient effect. This is an issue if you understand the mantle viscosity motion, including the grounding lines migration. Okay, and the second aspect of this poster is to really introduce this new open source 3D finite element GI modeling package called SICON SVE. This is actually already publicly available at GitHub, and so this is ongoing work, and welcome collaborations and all that. Thank you.
Okay, so now we're going to move into quick descriptions by people who don't have slides. So you just get to hear their voice and look at their face, I guess. Yeah.
Duncan Young again, University of Texas. My poster is basically a proof of concept of what you might be able to do in the interior of WAIS, looking at potential sites of subglacial volcanism. And yeah, stop by my poster if you want to discuss how we might be able to do this and how that might help with constraints on geothermal heat flow, GIA, and the question of what actually happened in the last interglacial in West Antarctica.
Hi, my name is Francisca Núñez Ferreira. I'm from University of Wisconsin-Madison, and I'm trying to understand the relationship between subglacial hydrology and sediment transport from esker deposits. And in my poster, I will be showing some results of the sedimentology of one esker located in Bayfield County, Wisconsin, and also some experiments that simulate the difference between confined and unconfined channels to see also the erosion and deposition difference between them.
What's up? I'm Sam. I'm a first-year PhD student with that dude. As Jeremy told you guys, the relationship between drag and glacier slip is important. And I'm looking not at the debris side of that, but the obstacle side of that, and trying to get a better idea of what the morphology of those obstacles, specifically quarried faces and quarried bumps, looks like, using machine learning from recently deglaciated surfaces to show that the method will work. I just don't really know how yet. So please help me.
All right, good morning. I'm Dan Morgan. I'm at Vanderbilt University, and my poster is a little different because it's all about dirt. And so that one dirt guy in here. And really what we're using are sort of provenance tools from the amazing record of glacial tills that are in the McMurdo Dry Valleys to look for evidence of changes in glacier flow in the past. So it's kind of a paleo ice flow project that we're doing. It's also a fun project because the field team that went last year was 3 undergraduate students and a postbac student. So it's a unique field team that it's all really young researchers. And the other exciting thing I want to briefly mention is if you're a finishing PhD student, a postdoc, come talk to me because we're doing a search for a climate scientist in our department right now. I just got this email from my chair today, and he said I could share it, that we're looking for a senior lecturer, so teaching track faculty, to come teach climate science, paleoclimate, atmosphere, ocean science, anything. It's a broad department, and so if you're interested in starting to look for jobs, come talk to me. Thanks.
Hi everyone, I'm Chase Shivers. I'm a postdoc at Woods Hole Oceanographic Institution, and I'm going to take you away from West Antarctica to go to Emery Ice Shelf in East Antarctica to look at a superglacial melt feature called an ice doline, which are basically just depressions left over from the meltwater draining. We take a bunch of compile a bunch of remote sensing observations, including Landsat imagery, ISAT-2 elevations, and some climate data from RACMO, et cetera, to sort of look at its observational history from 1973 all the way to 2022, see what may have led up to the initial collapse and drainage and its post-collapse evolution. So come check it out. Thanks.
Hi, everyone. My name is Dougal Hansen, fellow glacial dirt enthusiast. I'm at the University of Wisconsin, Madison. I'm a postdoc. Title of my poster is Constraining Subglacial Till Properties with Acoustic Techniques. In a nutshell, it's basically we're trying to better understand controls and the amplitude of reflected seismic waves off the ice bed interface. We think that this could be a valuable means of mapping subglacial effective stress in both time and space. And so these experiments are kind of new and just getting off the ground, so I'll be really excited to chat with you all about it and hear your thoughts. Thank you.
Hello, I'm Chris Pierce. I'm here from Montana State University in Bozeman, Montana. I'm a fifth-year PhD student, and the title of my poster is A Simulation Approach to Subglacial Hydrology. Basically, what I've done is taken a radar simulator and attempt to simulate the subglacial environment and what it would look like from a radar system, and then attempt to use that to infer the size and shape of different subglacial water structures that might be underneath and compare those to existing radargrams to kind of better understand the subglacial hydrology system. So come on, check it out, my poster.
Yeah, hey everyone, I'm Jamie Stutz from the Polar Rock Repository, a walking billboard here. Yeah, so I'm the assistant director there. Just to wave the flag for the Rock Repository, we have over 60,000 rocks from the continent, as well as dredge samples from around the Southern Ocean, and some dirt. So plenty of dirt to go around from the serious deposits that are collected along the Transantarctic Mountains. So not only do we have rocks for you, but we'd also like your rocks, so we can talk about that anytime. Leading a double life as well, so I'm a research scientist as well, and just finishing up some work on glacial reconstructions around the David, Bird, and Thwaites glaciers using cosmogenic nuclides. I've got quite a lot of erratics from around there, and hopefully that can be of use for some folks looking at things upstream. So yeah, come and check out the poster and we can have a chat. Thanks.
Hi everyone, my name's Kaylee. I'm a PhD student at UCLA. A lot of my work is kind of just inspired by the realization that, so I should say I'm an oceanographer. I look at ice shelf cavities. And so a lot of my work has been inspired by the idea that there's a lot of dynamics that are extremely important in surface mix layers and bottom boundary layers, as well as overflows, which can be thought of as kind of an upside-down version of a plume beneath an ice shelf. And basically applying all those processes to the ice shelf ocean boundary layer and plume, because they've basically been overlooked up till now. And seeing how these processes affect the stratification in that region, melt rates, heat pathways, and things like that. So please stop by.
Hi, I'm Sridhar Krishnan. I'm at Penn State University. So my poster is actually one that was put together by my colleagues at the Alfred Wegener Institute, Ole Zeising, Koen Hofstede, and Olaf Eisen. But I'm a collaborator with them on the GHOST project on Thwaites Glacier. This is a 200-kilometer long fiber-sized traverse. So yeah, come take a look at our first cut at what the bed of Thwaites Glacier looks like.
Well, always dangerous to follow up your PhD advisor. You can say whatever you want. But that brings us to a wrap. We have session break, and we're going to reconvene at 10:40. Is that still scheduled? Okay. And I think there's refreshments out here. Like I said, the posters are behind us. We have 2 dedicated poster sessions, but as was said earlier, you can treat all breaks as sort of informal postal sessions too to check them out. So thanks for everybody that talked, and we'll see you around.